Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk. It's been a long summer. And one of the other questions I got that I knew I wanted to talk to you about was from this person that had an electronic device, and I wasn't really clear where they were using it, yet it seemed to be in a harsh environment of some sort.
Okay.
And I think they're in oil and gas somewhere, but it wasn't really clear. And they have a system that has all of these limiters on it. So like if the temperature gets too high, it shuts down the CPU. It degrades its performance and eventually shuts it down.
CPU is all throttle based on a lot of them throttle based on temperature. They start running slower.
Yeah, and it doesn't create as much heat and all this other stuff.
Right.
And they also had vibration. There's some of their sensors were sensitive to too much vibration, and they would damage them. And so they would basically, it's like the old spinning hard drives, right? It would go into a safe position.
Right. They lock the arm.
Lock the arm so that it wouldn't be reading and writing, yet it wouldn't, in vibration or a shock, it wouldn't damage the disk. And so it protect itself. So and then the question was, I've got this system. It's relatively new design. We're early in the program. And all these things that we talked about last time, they were like, yeah, HALT would be a good idea to do. And then they were scratching their head and asked us that, well, how do we do it? if these things,
if you've got all these interlocks, right. And this is very common. This is like, many of the power supplies have a thermal interlock, a thermistor, or a thermal shutdown over temperature protection. And the first thing you need to do, because if you just leave that in there, you're only testing that sensor and when it's going to shut down. You don't really test what the capability of the system is without the sensors.
Right.
And I would say the same thing to whoever designed this product. I said, I would ask them, have they tested this without any interlocks on? They have some vibration level that tells it to shut down, or they have some thermal level that tells it to shut down because it's going to be damaged. Do they know where that actual empirical damage is level that it starts to occur, and how much margin they have from that point that's to protect it?
Go deliberately break the thing that you're trying to protect.
Exactly.
See what margin you really have, and are you setting your limits at the correct place?
And how that distribution is around that point, because we know there's variability in all these assemblies. So they're not all going to shut down at 101.5 degrees or 101 degrees. They're going to shut down at 90, 80, 120, maybe. Who knows? That's what you've got to establish to me. And this is why I look at HALT and the environments that we're using to stress the product may never occur in that product's life, but if it exposes a weakness and it establishes a margin, or you know what the margin is for that particular stress, it can accelerate other relevant things like vibration. Accelerates a solder crack or a crack. Thermal cycling also does the same thing too, but vibration
is a little bit quicker at it.
It does it quicker, and it's still going to break either way, but you find it sooner, and it's another weakness that you want to correct for. So I say establish without.
Well, how do you do that? I mean, in a practical sense, if it's built into the CPUs, do you have to have dummy chips made?
I dealt directly with that.
I thought so. That's why I'm asking.
Because, I would wish Intel would give me the key to the thermal diode inside the CPU that I could turn it off. And they weren't about to. They're not in good. It's programmed. They know what it is. They can shut it off. They could put give me the code that would disable it. But no, they're not. I'm sorry, even though you're with Dell and you sell millions of or chips, they're not going to do that. And the design engineer told me that, just forget it. You're not going to get that from them. So what I would do is I put a water cooled block because the CPU really wasn't a big issue, a problem in the reliability of
Mhm.
a PC motherboard. And so to override or to suppress that interlock, the thermal overprotection system, I would use a water-cooled block, which is now common in gaming computers, and
Mhm.
I'd run it into the chamber and just have it on that one device on the CPU,
On the chip,
and
yeah. And
and the
so
rest of
this, so the CPU could still operate,
the
but then
CPU could
your everything else is at the accelerated, the higher temperature or lower temperature or whatever.
right, and so then I would get, and almost always I'd get to an operating limit. It wouldn't destroy the unit, but
Hmm.
it would give me a blue screen of death or what
Or whatever.
microscope
Yeah.
a bug indicator is I think microscope anyway. So then I would shut it down and put another sample in, and I'd find a range of graphics cards or memory uh, DIMMs that I put in there, and they had different ranges depending on the manufacturer. And so that was another way of learning, the variation that sometimes components that I could easily interswap
Hmm.
would limit or uh, hold back the capabilities.
Yeah, I had one team that was a socketed CPU, and so they moved
Yeah,
it
that was
off.
common. That
They
was
moved
very
it off the
common.
board. They moved it out of the chamber, and they just got this massive threaded cable-ish thing that sat in the socket, and there's just a wire mesh thing that came out to the side, and there's this CPU hanging there.
Wow, that
And
to me is real
the timing
surprising.
issue, the issues
You're
with
right,
timing we ignored
right,
because we knew we screwed that all up,
right,
but it
right.
worked, and it allowed them to run the board and see all kinds of stuff on the rest of the motherboard.
Well, that's maybe one of the things you have to do. You have to be creative sometimes on
Yeah.
how to keep these things cool. Sometimes you can blow a like power supply that you can't remove the thermal shutdown. I would blow air. I'd build a chamber inside the chamber
Yeah,
and
just have
blow
a
air
cold
out.
air section of it. Yeah.
Yeah, and also because of that, like in storage technology, the read-write channels for the tape drives couldn't be very far away from the tape head
Hmm.
because of the speed of the signals. And so we had to build a little suspended box for the cables to go in and out of and not vibrate.
Well, we did that with hard drives, spinning hard
Right,
drives. We just
exactly,
pull it out of the
exactly.
box and suspend it on a wire or spring above the chamber, and it would get all the temperature variation, but it used its own cable. It was long enough to just get it, 2 inches above everything else, and it wouldn't
Right,
get banged around.
right. That's what's called a fundamental limit of technology. You can't vibrate a spinning disk. They didn't do it. Now, of course, solid state disk, you can vibrate
Daylights out of
crazy.
them.
Yeah,
Yeah.
yeah. They don't fail. So in fact, I put one in a laptop, Dell computer and
Hmm.
couldn't break it. I mean, it didn't stop. I cranked up the vibration table to 60 Gs and it was still running fine.
Wow.
Yeah. It's
Yeah.
people are surprised at the capabilities if they go to start testing, and they've never done this before with their designs. If they go to empirical limits, not theoretical, not the spec, but if they go beyond that, they sometimes discover that they really do have a lot of margin.
Well, that's my favorite part of doing HALT is you sit next to the design engineer or
Yeah.
developer or somebody and you say, so how far do you think it'll go? Oh, it won't go past 50C. No way. And we're at 80C. And says, well,
Yeah.
you're buying lunch today.
Yeah, and they're surprised and I say, look at all the room you have to test that you can do. You can establish how the parameters shift as you go up in this range, and that
Hmm.
can become like a prognostics indicator, in the future.
Yeah, I also always warn them, do not, whatever you do not send this report to your marketing team because they're going to
Yeah,
start saying it
exactly.
can do all
It's
this.
capable, right?
Yeah.
And your customers will be using it right on the hairy edge of its capabilities.
That's right. Like, yeah,
Yeah,
don't tell them that.
right. Don't tell them what you test to. And
That's right. Tell them, where you expect the customers to use it and they're okay with that expectation. Stay there, but make sure you have lots of margin after it. You don't need to tell them what margin you have.
right.
You don't have to tell them that. Please don't tell them that. No, really don't tell your internal marketing guys. They'll just go
Yeah.
ballistic on that.
You know, the failure data that we've talked about in the field, don't tell them about that either.
That's right.
You know,
Well, yeah.
yeah, there's stuff we don't share, and that's one of, of course, my problems with the reliability field. It's so sensitive that we can't really share a lot of that. You know, what kind of, what's the typical margin on your PWC, your printed
Printed
wiring
wire.
board assemblies, in capabilities? What are your operating? We think we can kind of get this database of, typical motherboard
Well,
PC.
we had stuff
Mm.
like that we had design guidelines at HB,
Yeah,
and there was all kinds of stuff internally that we said, this is good or not good. These are things to
right.
do or avoid. And for, things that we'd learned the hard way usually. And it became good internal practices, but they would not be published
Oh,
externally.
no, no. And I do the distribution of the temperatures of operating limits of different motherboards of different models of PCs that we built. And
Hmm.
I'm, not about to release that because it's something that the public would take and say, oh, it's capable of running at a
Well, I'm
hundred,
going to put it
hundred,
under my hood of my
a
car and let it run
100,
there.
yeah, exactly. 110C. No, it doesn't, folks. That's under very special conditions in a
Yeah.
chamber. But so yeah, it's something you almost always with some vendor power supplies. You're going to have to disable the thermal shutdown. You're going to have to, if you can. If you can't, then you're going to have to find a way to possibly uh, suppress that,
Yeah, suppress
cool
it
it.
or locally cool it.
All right.
But I think the point of, whenever you can turn off or disable those protections to see
Right.
what your margin really is and what
Right.
kind of
Right.
variability you really have,
Right.
that's harder in many cases, like with your description of working with Intel CPUs, is that you just had to cool it. That's a backup system, is locally cool it or isolate it or
Right.
separate it. Now, besides temperature and vibration, what other types of stresses have you seen? I've seen like ESD protection, although I don't use ESD as a stress very often in HALT testing,
Yeah. Yeah.
but electrical, surge suppression, stuff like that. Um, have you ever tried to disable some of those?
No. No, I've never had that an issue. Um,
Plenty of things got through
but
anyway.
I do definitely power cycling during halt
Hmm.
is a critical finding out,
In
where
rushes
that
and all that.
operating, where you can boot it up or where you can shut it down and boot it up
Hmm.
and let it cool down. So, but no, I've never had to do that. As far as moisture, I've never had a moisture detector
Well,
that
I've
I've
done
ever.
freeze thaw separately from HALT and some products that where it was in the environment where it was going to see freeze and thaws.
Yeah,
And that's like orders of magnitude more damaging than just the thermal cycle on a circuit board.
right.
When it's outdoors and it's going to see minus 40 and then warm up to, 40 degrees. And I did a big study for one client. They were in a high desert area, sort of like where you live,
Yeah.
and where
Yeah.
the and we were trying to figure out, well, what is the ambient, daily change in temperatures? I pulled a bunch of 20 years worth of weather data from various
Uh-huh.
stations in that area,
Hmm.
and it was on average, it was a 20 degrees C change in temperature every day. Now, seasonally, it'd be colder and hotter and stuff like that. But every now and then, they would have like a 35, 40 degrees C change in high to low. Some days were just off the charts of how much they moved.
All right.
And you know what it's like in Colorado.
Yeah, it can be extreme. We get, extreme cold, but not so much extreme heat. But no humidity, very
Yeah.
low humidity most of the time.
But when the sun comes out, it heats up quickly. And I'm thinking these
Right.
were solar panels, and they're meant to be in the sun, kind of. And
Right. Right. And they
when
get
they
up.
would go from, overnight low of say 25 degrees Fahrenheit, a little bit below Celsius, and the sun hits it, and then they turn on and they're working, so they're creating some heat, and then
Right.
that panel would be at 40 degrees C by noon. And
Right.
it's like that is some thermal cycling. And
Right.
there's not a lot of room there to do an accelerated test to check for delaminations and everything else. But that's why we're doing it.
No.
We're trying to figure out what is the actual range. And then it was an inverter box sitting there cranking out all this power with this IGBT, all this heat out of it. And it's like, you got to vent this somewhere. You can't, this is going to melt the box if you don't vent this to the outside. Well, there's too much dust and this, that, and the other.
Yeah,
It,
I think that, that in solar panels and certain other energy generation systems, it's, the long-term wear out is of critical importance. And
oh,
that,
yeah.
the fatigue damage over time, I think that, of course, I've seen and been to solar panel test facilities, and they,
Hmm.
where they have the hail gun, where they shoot ice balls directly at,
And there's an
really
art to
hard.
making really good ice
Yeah,
balls. I said, can
yeah.
you teach me how to do that for my whiskey tonight? I want a
You
nice
know,
clear ice
those,
ball.
right. Those are not typical tests you'd run on a PC motherboard. But
No, you
yeah,
don't fire
yeah, yeah.
2 inch hail.
But in that case, I didn't ask them if they, find the limit of what that capability is, and
Hmm.
because they can't prevent for everything, and certainly can't prevent a tornado from ripping up a
Yeah.
solar farm, but you know, they should have an idea of where those limits are, and with that, they can do more rapid thermal cycling. The compression of the cycles instead of
Hmm.
waiting day and night like you do in the field. But we also have a long history of field experience with solar panels, and I expect as some of them are dismantled and removed after 10 years, some of them I'm sure have been operating that long,
Oh,
or
yeah.
whatever it is, that they go back, and those are again gold for future
What's working,
evaluation.
what's not.
And
Yeah.
yeah, and do cross sections, look at every possible interconnect in there and see what's fatiguing the fastest or what they can improve.
Yeah.
And of course, the power of efficiency is increased, significantly on
Oh,
those
yeah.
cells.
Yeah.
So they may be replaced because of that in the future. I don't know.
But it's interesting when you build a product and you want it to be for whatever this application was, is they said we know it's going to get these stresses, so we're going to have all these built-in protections. And like you said, CPUs have been doing this forever.
Right,
And and there's all kinds of things we do on systems to take down spikes, the electrical spikes or
right.
jolts, and we do all kinds of stuff to take care of all these different threats that come into a product, which is
Yes, but
fine. It gives us a robust
right.
system to survive.
But establish what the margin you need. I mean, find out without these protections what the limits of that board are,
Hmm.
and then where this, you can really safely put the protections and maybe beyond what you expected, or maybe even smaller than you expected.
Yep.
Anyway, you've got to determine the real empirical limits before you um, have an idea of how much margin you have. Also, again, the way I look at HALT is not from a perspective of what the outside environment is going to affect or how it's going to impact, but how stresses can show me the weaknesses that if I
Hmm.
find them, then I can establish, for this environment, is this going to be a problem? Is this going to be something we need to boost? Because,
Hmm. Hmm.
like you said, some things might be under a hood of a car, and that's even worse. Just think of that here in Colorado,
Oh, yeah.
where you're in, minus 20 Fahrenheit, and you got to go,
You fire up the engine and it
and
warms
you're
up,
right.
and
Yeah, you got 100, easily 100 C. But so that's, that's kind of the philosophy and Greg Hobbs, who created the AHA concepts, really wanted to say, look, don't look at the outside environment yet, but look at the fundamental limits of technology and what strength you can build, what strengths is in the product, and whether that can be improved or whether those things that you can improve will be affected, can be suppressed or, protected against. Because some things you may not be able to, like, you can't change the capability of an LCD under thermal conditions.
Right.
I think they've gotten better, but they're always going to black out.
They still go blank when they get cold enough.
So that's fine. You can't change everything. You can't make everything. You got a fundamental limits of current technology, and it's getting better. Like right now, a drop test for a phone, I would expect it should be able to take a 6-foot drop without breaking and without a case.
Just give it to a teenage daughter.
she's now
be broken by the end of the day.
Yeah, right. She's getting older, but she's 22 now. So, but she's doing it with our car.
Oh, ouch.
Yeah, she's pushing the limits of that with the oil changes.
Okay.
Anyway, so
all right, well, cool. It's a common problem, as you said, and
you're almost always going to have to defeat some interlock on the way, and just realize that this is the way to establish a benchmark for the raw hardware and the raw item,
design,
and not testing the shutdown overprotection sensor. That's what you're doing if you just
let it just shut it down. It works. Okay, fine. we didn't learn anything there.
Yeah, we learned that the sensor shuts it down. Fine, that's great. Okay, but we don't know
we don't know what else.
But if 3 degrees higher would have caused the damage to happen on the board,
then we don't have much margin there. That's the problem.
That's right.
All right. Well, that's cool. It's so that was one of the other questions that came up across my desk anyway this summer. So I'm quite sure I'll dig up some more, and we'll have plenty to talk about next time we get together,
sure.
Kirk. And but if you're listening to this and got a question, we as always are looking for questions, and even when I'm not promoting the questions, the other hosts of the show do, and we all enjoy hearing from you and getting some sense of what you're facing and what kind of challenges you have. So let us know. Head over to accendoreliability.com/go/SOR. You can find a couple of different ways to get in touch with us. Kirk and I and the other hosts of the show are available through LinkedIn and our About pages. So plenty of ways to get your thoughts over to us. We really look forward to hearing from you. So with that, Kirk, I think we'll not push the limits of our listeners' patience with us and call it an end of a show.
Yeah, I think I'll go test some pinball machines.
There you go. Have fun, Kirk.
All right. Take care, Fred.
All right. We'll talk to you later. Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.